For decades, our computers have kind of followed this one simple rule. Get smaller, get faster, get more powerful every couple years. It's something we've all just gotten used to. But what if I told you that incredible progress is about to hit a brick wall? In this explainer, we're going to look at what comes after silicon. Is the future of computing really going to be built on carbon? Right? Let's get into it.
And it's a really good question, right? We've all just come to expect this relentless, nonstop pace of innovation. But what if it just stopped? What if the very laws of physics that let us build this amazing digital world are now the exact things holding us back?
So the engine that's been driving all this progress, it actually has a name, Moore's Law. You've probably heard of it. It's this simple observation that the number of transistors we can cram onto a chip doubles about every 2 years. But to keep that amazing trend going, we have to keep shrinking those transistors. And we've gotten so good at it that they're now just a handful of atoms across. And at that tiny scale, well, things start to get really weird.
And that weirdness, it brings us right to our first section, hitting the silicon wall. We're literally talking about the fundamental limits of the material that has defined, the entire modern age.
See, when you shrink silicon transistors down below about 22 nanometers, physics it starts working against you. The little barriers that are supposed to control the flow of electricity, they become so thin that electrons can just tunnel right through them. It's a real quantum effect. And this causes all sorts of problems, like current leakage, which wastes a ton of power even when the transistor is supposed to be off. Plus, at this incredibly tiny scale, even the slightest little variation in manufacturing can make one transistor behave completely differently from the one next to it. It's just unpredictable. Okay, so if silicon is running out of road, what's the alternative? There has to be something else, right? Well, that brings us to the potential hero of our story, the carbon nanotube.
A carbon nanotube field effect transistor, or let's just call it a CNT-FET for short, is actually a deceptively simple idea. You basically take a standard transistor and you swap out the most important part, that's the channel where the electricity actually flows, with a tiny hollow tube made of carbon atoms.
So how do you even picture one of these things? Okay, think of it like this. Imagine a sheet of chicken wire. That honeycomb pattern, that's kind of like a material called graphene, which is just a single layer of carbon atoms. Now, take that sheet and roll it up into a perfect, seamless tube. Boom. That's a carbon nanotube. It's an incredibly strong, incredibly stable structure that is literally just one single atom thick. It's amazing. Okay, but here's where it gets really interesting. Not all nanotubes are created equal. Their most important property, how they conduct electricity, depends entirely, and I mean entirely, on the angle you use to roll up that graphene sheet. And this is just a brilliant way to see the difference. If you roll that sheet straight on, you get what's called a metallic nanotube. It acts just like a tiny copper wire. Electricity just flows right through it, no problem. But if you roll it at a very specific angle, you create a semiconducting nanotube. And that is the magic ingredient. See, a semiconductor can act like a switch. It can be turned on and it can be turned off. And that is the fundamental job of every single transistor in your computer. The properties of these semiconducting nanotubes are, well, they're almost perfect for making a transistor. They allow for something called quasi-ballistic transport. Now that's a fancy term, but it just means electrons can basically fly right through them with almost no resistance at all. They're also super stable chemically, they can handle huge amounts of electric current, and they're fantastic at getting heat out of the way. So yeah, this material has absolutely incredible potential. But how do you actually build a working switch out of something that is literally thousands of times thinner than a single human hair? Well, scientists have made some really huge progress here. The early designs were pretty crude. We're talking basically just dropping a bunch of nanotubes onto some metal contacts and, hoping for the best. The first major leap forward was the top-gated design. That's where they could finally isolate a single nanotube and build a really precise control gate right on top of it. But today, the absolute cutting edge is the gate-all-around design. It does exactly what it sounds like. It wraps the gate completely around the nanotube for just maximum performance and efficiency. Okay, so we can build them. That's a huge step. Now it's time for the main event. How does our new carbon challenger actually stack up against the reigning, defending champion, silicon? Let's just start with the big, impressive number. The very first sub-10 nanometer carbon nanotube transistor. It delivered more than 4 times the current of the very best silicon devices at the time. So what does it actually mean for you and me? It means we're looking at the potential for processors that aren't just a little bit faster, but are way more powerful and efficient. Think about complex AI models running right on your phone instead of in the cloud. or batteries that last for days, not just hours. That is a massive leap in performance. And when you look at the data head-to-head, it gets even clearer. Let's take a key metric like on current. That's basically how much electricity it can push when it's switched on. The CNT FET is about 3 times better. Or how about carrier velocity? That's how fast the electrons move through it. It's about twice as high. Now, this isn't just about making your apps open a fraction of a second faster. No way. This kind of raw performance boost could unlock entirely new forms of computing. We're talking about everything from truly seamless virtual reality to complex scientific simulations becoming way more accessible.
So, the crucial point here is this. CNT FETs aren't just some minor, incremental improvement. They represent a fundamental step change. We're talking better control over the channel, way higher electron speeds, and much, much greater power efficiency. It's the kind of leap forward that could completely redefine what our devices are even capable of doing. But, and you knew there was a but, right? This is the billion-dollar question. There are some major hurdles. For one, they can be a bit fragile, sometimes breaking down under high electric fields. It's also incredibly difficult to get a pure batch of only the semiconducting nanotubes you need. You pretty much always end up with some of those metallic ones mixed in, which can short out your circuit. But the biggest problem of all? The real showstopper? Mass production.
And that brings us to our final and probably most important section. What does all of this actually mean for the future of computing? You know, this quote from the source material really just says it all. We know carbon nanotubes have these amazing, unique properties. The science is solid. The problem, it isn't really a science problem anymore. It's an industrial engineering problem. The question is, how do you go from making one perfect little transistor in a clean room lab to making trillions of them flawlessly on a factory floor? Right now, the most promising path forward is this really mind-bending idea called self-assembly. So instead of trying to place every single nanotube with some kind of microscopic robot arm, the idea is to use chemistry to guide billions of them to arrange themselves into the perfect circuits. You're essentially teaching the materials to build the chip for you. It sounds like science fiction, but it might be the only way. Which, of course, leaves us with this final, huge question. Carbon nanotubes. They offer a clear path past the physical limits of silicon. They promise a whole new era of smaller, faster, and way more efficient electronics. But standing between that incredible promise and the devices in our pockets is one of the greatest manufacturing challenges of our time. Whether or not we can solve it will be what determines if the next age of technology is built not on silicon, but on carbon.